Hello, everyone. My name is Olivia Chitarra, and I'm a second year PhD student at ISMO in France, and I'm working with Marie-Aline Martin and Olivier Pirali. And today I want to present you a new investigation of the pure rotational spectrum of the hydroxymethyl radical, CH2OH, to enable its interstellar detection. But first, why are we interested in the study of this radical? First, as you can see on the figure right in here, the radical is composed of very important astrophysical elements, which are carbon, hydrogen, and oxygen. Also, there are several theories that imply the radicals. On the left side, for example, you have a gas phase reaction that could produce the radical from methanol. On the right side, you have a representation of a dust grain, so the solid phase of the interstellar medium, that is composed notably of methanol. And this methanol could dissolve the radical after UV irradiation or cosmic rays. Finally, on this figure, you have a mechanism that explains the formation of glycolaldehyde or ethylene glycol, so complex organic molecules, and this mechanism implies the CH2OH radicals. There is another thing to note on this figure that is very interesting, is that all those species have been detected in the interstellar medium except the CH2OH radical. Even the isomer of this molecule, the methoxy radical CH3O, have been detected in the interstellar medium. So really, the CH2OH radical is a missing link in the interstellar chemistry. But to be able to detect the molecule in the interstellar medium, astrophysicists need high-resolution studies. The first one was actually a raw vibrational studies performed in the infrared spectral region with a supersonic jet in 2013. The actual first rotational studies was performed in 2017 in the millimeter wave spectral region by Bermudez and al. And during this study, they were able to observe for the first time the rotational tunneling spectrum of the radical. During this study, they were able to measure approximately 100 transitions that are marked with these asterisks. So as you can see, they were able to measure all intense transition at room temperature at 300 Kelvin. But the radical is expected in cold environment of the interstellar medium. So if we focus on the prediction on the cold conditions, so around 10 Kelvin, you can see that transition expected to be intense are not the one that are intense at room temperature. For this component right here, this transition is the small component, so they are more complicated to study at room temperature because they are very weak. So these first rotational studies only gave prediction of those transitions important for astrophysicists, and maybe this lack of experimental measurement of those important transitions could explain the non-detection of the CH2OH radical yet. But the study of this radical is complicated for two main reasons. The first one is the complexity of the spectroscopy. As you can see, the radical is an asymmetric top molecule with a planar vibrational ground state. It's a radical, so you have one unpaired electron. You also have three hydrogen of non-zero nuclear spin. And finally, as it was shown by Bermudez and al. In 2017, you have a tunneling of this hydrogen. So one way to represent all those effects on energy level is to begin with the rotational level described by N, K, and Kc. First, we have to consider the interaction between the tunneling and the rotation that lead to a splitting of the rotational level into sublevel, into ortho and para level, depending on the parity of K plus V. Then we have the interaction between the electron spin and the rotation that leads to another splitting of both ortho and para level. And finally, different coupling between non-zero nuclear spin of hydrogen and the rotation leads to an hyperfine structure that I represented in orange with a number of sublevels different for both para and ortho level. So let's take an example of what it means on actual rotational level. So on the left side, I'm representing all those successive splitting for the 10-0-10 rotational level. And on the left side, I'm representing those splitting from the rotational level 10-1-9. And now I will only take one rotational transition, a RQ transition between those two rotational levels. And as you can see, we actually obtain 4 clusters of line. We have 4 different clusters for one rotational transition. So you have the cluster in purple, in blue, in red, and in green. So we need to perform a systematic measurement of all cluster of all components for each rotational transition. There is another difficulty for the study of this radical. It's on the experimental side. It's a radical, so it has a relatively high chemical reactivity and a relatively high short lifetime. So what I present you right now is an optimized version of the experimental setup. So first, we are using a selective method to produce the radical by a nitrogen abstraction with from methanol by a fluorine atom. So we are producing fluorine atom with a microwave discharge that will selectively attack hydrogen of the methanol precursor. So it will selectively produce CH3O and CH2OH. Then to record the room temperature gas phase rotational spectrum, we're using a frequency multiplication chain spectrometer covering the 140 to 900 gigahertz. And finally, we're also using a magnetic field modulation to distinguish line arising from closed and open shell species. If you want more detail about all the optimization we did on this setup, I invite you to see Jean Thibault Spagnol talk. So let's go back on the example on the energy diagram I gave you previously. So I told you it was necessary to measure all cluster of line, all component of each rotational transition. So for example, for this rotational transition, that's what we did. We actually measure all components, all 4 cluster of line, the red one, green, blue, and purple. It's not very easy because all those transitions are spread over 1 gigahertz, but it was necessary to perform this systematic measurement. So after all those measurements, we were able to measure approximately 700 transitions that we added to the 96 already measured by Bermudez and Dahl. And all measurement was made with a frequency accuracy from 50 to 800 kilohertz, depending on the spectral range we were measuring. Finally, we were able to measure transition involving N from 1 to 17 and Ka from 0 to 2. So thanks to all those measurements, we are able to obtain a more reliable, a more constrained fit, a more constrained set of rotational parameters. So I give you this table right here, where I compare the last investigation we performed up to 900 gigahertz, all the measurements we already published in 2020 compared to what was obtained by Bermudez and Dahl in 2017. First, as you can see with the RMS that we have presently, it's a good RMS, but it's good, but it's not as good as what could be expecting from experimental accuracy. That could be explained because we are not using the best model. We actually using a Piquet reduced axis system Hamiltonian, and it's not the more suitable model that could be used. So if you want more detail about a new model that is more suitable for this radical, I invite you to see Laurent Couder's talk that will explain you the new model to describe these molecules. But if we stay on this model, I give you a rotational constant, so ABC, quartic centrifugal distortion constant, DNK, and Nipperfine interaction constant, AF. For this last constant, you can see that we are in quite good agreement with previous studies. But it's not the case for the rotational constant or for the quartic centrifugal distortion constant. We have quite a strong deviation from what was measured. And this deviation have a quite important consequence. For example, this deviation leads to this shift of line position. So we have a shift, if we compare to the previous simulation, of around 10 megahertz. And it's a very important shift because it can prevent astrophysicists from detecting the molecule in the interstellar medium. So finally, we also focused, the second input of our work was the measurement of astrophysical relevant transition. So in pink, I represented all the transition predicted at room temperature. And with the asterisk, I represented all the measurements performed by Berbenes and al. In 2017. During our new investigation, the one already published in 2020 and the new ones, we were now able to measure transition up to 900 gigahertz, but we also focused on the measurement of transition expected to be intense under cold environment. So at 10K, you can see in dark blue, that we were able to measure those astrophysical relevant transition. For example, this transition that was expected very weak at room temperature, we were actually able to measure it. It took several hours, and the signal to noise ratio is not the best one, but we were actually able to measure those very important transitions for astrophysicists and for the interstellar detection. So finally, during our new investigation, we were able to obtain a more constrained set of rotational parameters, allowing us to obtain a better prediction of line position. But we didn't use the best model, and we still have some problem with this model. So now we want to use a more suitable model. But experimentally, we were able to measure transition up to 900 gigahertz. Also, we focused on the experimental measurement of astrophysical relevant transition. So transition expected to be intense under a cold environment. And this experimental measurement allow now confident search of the CH2H radical in the interstellar medium. And the detection or the non-detection will imply a modification of astrophysical model if it's actually in the interstellar medium or if it's not. So finally, I want to thank all my collaborators, all the people that work with me on this project, and all funding agencies. Thank you very much.